Hi everybody. Just wanted to give you a brief rundown on the flip-flop conversion thing. What we have here is a little matrix that I drew up. The SR, JK, T, and D flip-flops are in the vertical axis, and we're going to make these using SR, JK, D, and T flip-flops. What you notice in a 4x4 is you have 16 different ways to make stuff, but in fact you don't want to make an SR flip-flop using an SR flip-flop, or make a JK using a JK, or make a D using a G, or make a T using a T. So you take out the main diagonal. That gives you 12 different activities which you can engage in. And as you go through each one of these activities, you can in fact check off as you go. And that's what we're going to do. What we'll do is we'll take a fresh piece of paper and keep this off on the side here. And we'll refer to it from time to time. But we'll start off by writing out a D flip-flop, the present state, and then the next state, and as you know, if the D flip-flop is a 0 on input, the next state is going to be 0. If it's a 1 on input, the next state will be 1. And now what you do is you look at the present states and next states and come up with what are known as the remapped excitation table. So you start off by looking at the T flip-flop. To obtain a hold state, T puts in a 0. To obtain a change in state, T puts in a 1. And similarly, here's a hold state, and those are the remapped inputs for a T flip-flop. If you wanted to do something like that for the SR flip-flop, what you can do is you can make the argument that if you're in the reset state, and you want to stay in the reset state, make sure you don't assert set. Reset, we don't care. Similarly, if you're in the set state and you want to stay in the set state, you do not assert reset. But for the set state, we don't care. If you want to reset the SR flip-flop, then you have to assert the reset line and do not assert the set line. And if you want to assert the set state on the SR flip-flop, then you can assert the set line, do not assert the reset line. Similarly, we make these arguments for the excitation table on the JK flip-flop. The 0x, x0, works the same. But if you're in the set state, and then you want to change your state, you can assert the input to be 1, 1, because it turns into a toggle. Or you can assert 0, 1, because that'll assert a reset. So that means you get a don't care 1, and similarly, we get a 1 don't care. Now with these excitation table inputs, the remapped excitation table inputs for the various flip-flops, we can now proceed to do our constructions. So let's start off with a simple two-variable K-map and see if we can find out what the T function is equal to. And so what we'll do is we'll put D and Q over in here. Got an extra line in there. Forget about the extra line. Sorry for the blemish. Number your K-maps. Fill out 0, 1, 1, 0. And now what you see is T is equal to D exclusive or Q. And so what you can do is you can write out a little T flip-flop. And put in D exclusive or Q. And now what you've done is you've Let's get our little matrix. Used a T flip-flop to make a D flip-flop. Similarly, you can obtain the S as 001x. And now S is equal to D. You can obtain the R and write x100. Now R is equal to D prime. And what that tells me is that if I have an SR flip-flop, I can make a D flip-flop. So now we've got making a D using SR. Last one is JK. And we can write 0x, 1x. And we just did that one. It's x1, x0. And there you go. So now you can do the same thing for your JK flip-flop that you did for your D flip-flop. And your SR, sorry, the same thing for the JK flip-flop that you did for your SR flip-flop. And so now what you've got is you've made a JK from a D. You made a D from a JK, sorry. Using a JK, you made a D. There. And so that's the basic theme behind doing these sorts of things. The next obvious step is to switch your flip-flops. So now let's try something a little bit different. Let's try and make a let's try and use a JK flip-flop, or make JK flip-flops using different other flip-flops. That's probably the better way to say it. Q plus. So we'll use a variety of different flip-flops, but first we need to know the JK inputs, and we'll call this hold, call this reset, we'll call this set, and this will be my toggle state. And so when we're in the hold state, we just copy the present state over. This is reset. That's set. And this is going to be toggle. Now we can write out what does T do. And if you want T as a remapped flip-flop input based on the state change, this is a 0. This is a 0. It's a 0. It's a 1, 1, 0, 1, 1. For your D, you just copy the next state. And then for your SR, if you want the inputs to not change, what you do is you use S0X, and here we can use the same thing. And when the inputs don't change and it's 1, 1, it's X0. And when you want to do a set, it's 0, 1, or 1, 0 if you want to reset. And this is going to be a set operation. And this is going to be a reset operation. And I think that gives you all of the different combinations for the SR. And now your modus operandi on that is to do a 3-variable K-map with J and K. Notice how I always number my K-maps. And now when I go through and try and write out something like T, it's 0, 0, 0, 1, 1, 0, 1, 1. And now I can write out T equals and you can loop here, and you can loop there. For that loop there, that's going to be K, Q. And this here is going to be J, Q prime. Okay, got that right. So now you've got a mechanism in place whereby you can proceed and do all of the other flip-flops. Let's try and do the D. And we'll go through the D. 0, 1, 0, 0. 1, 1, 1, 0. And we'll do D equals. And then we can loop it. How shall we loop it? Well, let's see. We can loop like this, and we can loop like that. That's not too bad. And now if you loop like that, it's going to be JQ prime. Or it's going to be K prime Q. And so now it's J exclusive OR with K. Yeah. Well, it's probably going to look like this. you've taken the opportunity to make a JK flip-flop from a D flip-flop. You've done the same thing for the T flip-flop. You're going right along the row. The one thing you didn't do was an SR flip-flop, and for that you would need two K-maps because you've got two inputs, one for the S and one for the R. Zero X 0 0, 1X 1 0, and similarly you'll do another K-map just like that. This one will be for S and this one will be for R. Zero X X 1, X 0 0 1 0. Now you got to do your K-map looping. S equals JQ prime. Oh, that sounds familiar. And R is going to be equal to K Q prime. Oh, and there's another one. And so now that looks like J prime, sorry, yeah, J prime Q. That's very interesting. That was 0x 0 0, 0x 0 0. Just checking my work. 1x 0 1, 1x 0 1. Right, you don't need to loop those x's down there. They're the don't cares. So I think that looks pretty good. And so that's how you go through the rest of the row. And now you can do the rest for on your own. This is the basic procedure for implementing one flip-flop using another flip-flop. Thank you.